All right, everybody, so I'm going to be attempting to produce some video content that mimics what we were going to cover in class today. We have a couple of big points to make still to derive these big equations we're going to use for the rest of this chapter. The derivation is really important simply because it shows you what the equation means and how you can use it in different situations. And that's the biggest thing here. When we get the equations, how can we use them? What different versions are there that we can use? As a reminder, we were taking some general rigid body here on the left, and we had some origin that we started from in this rigid body, and a variable point B, to which there is a position vector, RB with respect to O, labeled here. As we consider every point in the rigid body, the point B will change and the position vector will be different. The calculation that we were focused on yesterday, well, Friday I suppose now, is the integral you see on the right, the integral of r cross a dm. This integral is helpful, I claimed, because when we write out what the acceleration of b is, this integral will have the alpha term not cancel out. And we'll see that as we work through the derivation. So that's our goal today. That's what we're working through. This is the right side of Newton's second law applied to all of the particles in the rigid body and then added up. As a reminder, that made the internal forces cancel out. So this is the right side of Newton's second law. The left side is going to be the sum of the torques about point O on the rigid body. But we're going to focus on this. First of all, the acceleration of B can be found relative to point O in the following way. Acceleration of B, this is not going to be enough space. I'm going to erase that and move down the page. Sorry, everybody. The acceleration of B is equal to the acceleration of O plus the acceleration of B with respect to O, which is circular motion about O. That's omega cross R, B with respect to O, plus alpha cross R, B with respect to O. This is the general equation for acceleration of A with respect to O. The relative acceleration of the two right terms, and the actual acceleration of B is this entire expression. I'm going to substitute that into the above integral, so this becomes the integral of R, B with respect to O, crossed with AB, which is all this, A0 plus omega cross R, B with respect to O, plus alpha cross R, B with respect to O. And we are going to simplify this as much as we can. This integral is still being performed relative to, over the mass of the rigid body. So I'm going to treat this integral one at a time. We're going to distribute the cross product of R with each term here and write three separate integrals, and we're going to tackle them one at a time. So this is going to be a big equation that we will come back to. I'm going to put a little star next to this. We're going to come back to this when we handle the derivation of each individual term. The first term is the integral of r, b with respect to the origin, cross a naught dm. In this, the acceleration of the origin does not change as we move through the object, and so this is equal to the integral of r, b with respect to the origin, dm, let me make some space for that, dm crossed a naught. The left integral can be replaced with the center of mass because the integral of r dm is equal to the position of the center of mass, g, with respect to O. I'm going to label that point in our rigid body. I'll put it here. As I pointed out on Friday, the center of mass symbol looks like this, and I'll label this as point G. G is the center of mass. So this is equal to M times RG with respect to O crossed with the acceleration of point O. This no longer has an integral, and we will go ahead and leave this term as it is. This is as simple as we're going to make this term for now. The next term is the integral of RB with respect to O crossed with omega cross R B with respect to O. And this term is rather complicated. It's a bit of a bummer, because there's an R on the left and there's an R on the right, and we can't pull this out in any meaningful way. The omegas are constant for the entire rigid body, but I can't pull them out. They're in the middle of this, quadruple cross product going on. So I have to think of a way to simplify this expression. On Friday, we pointed out the relationship for the triple product is the following. Well, A cross B cross C is equal to, so in this, that's why. Ha! A cross B cross C is equal to, I have to think of this equation here for a minute, make sure I don't make a mistake. C dot A times B minus B dot A times C. I'm confident this is correct. So, as confident as I can be at this moment, this triple product can be applied to simplify, quote unquote, the expression above. So I will. I'm going to first tackle the omega cross R product. So we have the integral of RB with respect to O crossed with, according to this, C dot A is the first term, that's RB with respect to O crossed with omega, not crossed, dotted with, dotted with omega times omega minus omega dot omega, which is simply omega squared, times RB with respect to O. So, I have this expression now. This is still integrated over the mass, and as we work through this, I want you to continue to consider how R is changing over the integral. That's the thing that's not constant. We can't pull it out. So, with this written down, how does this simplify? Well, first of all, the second part of this part is in the RB with respect to O direction. And so is this. When you cross two vectors that are parallel, you get 0. So when I distribute this cross product through, distribute into the two terms, this term will not matter. No matter what, that term goes away. And that's convenient. RB with respect to O cross with RB with respect to O is 0. No matter where you are in the object, those two terms are parallel. The cross product is 0. So we have this other term remaining. I will then write this as the integral of RB with respect to O crossed with omega, crossed with omega times the vector RB with respect to O dot omega. I moved some things around there, but there's no problem. This right here is a scalar and can be brought out front or behind or whatever. It can be multiplied whenever you like. So I did the cross product of RB with respect to O, cross with omega, then times this expression here. That's all that's left. In 3 dimensions, this term is a little bit problematic. R with respect to O and omega crossed, this gives a term that's non-zero in general. And additionally, R with respect to O dot omega is non-zero in general. When integrated over the mass, this is problematic. But in 2D, R with respect to O, that is a vector that goes from some place in our rigid body to some place in our rigid body. This is in the xy plane, and omega is in the z direction. So when we dot them together, this is 0. So in that situation, we have that all of this in 2D equals 0. This whole thing, the second term canceled out because R and R are parallel. The first term canceled out if we're in 2 dimensions. So this just goes away. It doesn't end up mattering. What actually goes on with this expression is a little bit more involved. Dealing with this when you're in 3D is not something we're going to consider, but it's something that we would need to consider if we're working with 3D objects. And in general, we do. So, with that in mind, we have now completed the first 2 terms. I will highlight the ones that we've finished. So, we have completed this term. Wow, that is a real regret, filled with regret. Let's undo that. Change our, maybe like something like this. Can you tell I am very well experienced? Okay, so those 2 terms, all done. Now we need to move on to the last term, and this is the term we actually care about. This term is the term that I said wouldn't cancel out. It's the one with the alpha in it, and I want to solve for it. Okay, so let's solve for it. New page. All right, great. So this is the integral of R b with respect to O crossed with alpha b with respect to O crossed with R b with respect to O integrated over the mass. We're going to use the triple product formula for this again. This is going to be equal to R b with respect to O dotted with R b with respect to O times alpha. Oh, I wrote b with respect to O here for alpha. That doesn't make any sense. I'm going to erase that now. Oh, I erased too much. Oh, no. Gosh. Okay, good. All right. So this is the integral of this, then minus R b with respect to O dot alpha times R b with respect to O. There's that triple product formula that's on the previous page as well. This is all integrated with respect to mass. In 2D, we have the same simplification as before. In 2D, RB with respect to O is in the xy plane, and alpha is in the z direction, so this dot product is equal to 0, so we're going to get rid of it. I want to emphasize that this would not be true in 3D, and this problem becomes significantly more complicated in 3D. This is the source of most of the confusion, most of the challenge. The previous example, the previous term rather, when I said that this term wouldn't cancel, that is its own thing, that has its own complications. This is the main source of complication right here. All right, the first term is also a little bit more simple. Look at the dot product. The dot product of a vector with itself is simply its magnitude squared. So that means that when I'm done, this is equal to the integral of R b with respect to O squared. Oh, let's get rid of that vector symbol atop its head. R b with respect to O times alpha integrated over the mass. Alpha is constant in the object. There's only one alpha, so I'm going to pull it out of the integral. I'm going to keep that vector symbol on it. Alpha times the integral of R b with respect to O squared over the mass. All right. that is the end of it. So we've completed every term. I'll go back to my previous page. We are now finished with all three. Wow. I forgot. How quickly I forget. We're finished with all three. We have all three done. And now I'm going to write the final expression. The final expression is this term here and this term here. So the sum, I'm going to leave off the relative thing. We understand moment of force, been working with it for a long time. The sum of R cross F is equal to this term, M, R, G with respect to O, crossed with the acceleration of the origin we chose, plus alpha times the integral of R squared, B with respect to O, integrated over the mass. All right. This right here is an expression we have seen before. We have worked with this before, integral of R squared dm, but even if we hadn't, this is an involved integral, and we can't put it in terms of the center of mass. There's no meaningful simplification to be done there. So, since there's no simplification, we just need to figure out what this integral is. This is called the mass moment of inertia. We're going to use the symbol I for it in general. This, as written, is going to be I about O. You have encountered mass moment of inertia in your physics classes. We've done area moment of inertia in statics and mechanics of materials if you've taken that class. They're related but not exactly the same. The important thing is it's an integral of distance squared over something, in this case mass. This equation is the final equation. So I'm going to write it just one last time. The sum of the moments about point O is equal to the mass times rg with respect to O crossed through the acceleration of the origin plus I alpha. This equation says it's a vector equation right now, and it is, but I want to emphasize that it points in the z direction in a 2D problem, right? This term alpha, the last one, I alpha, is definitely in the z direction because alpha is in the z direction. The term to the left of it, RG with respect to O, is in the XY plane. AO is in the XY plane, so it's in the Z direction too. Everything here is in the Z direction. So it's kind of a scalar equation, but you need to think about carefully about the directions in which things point. So we'll leave that alone until we get to specific examples. This is the big equation. This is the one that I want you to know. Applied to specific examples, we have a couple of different ways to apply this equation. And now I'm going to work on those couple of different ways. The first way, well, let's write the general equation first. So general equation. The sum of the moments about point O. This is the equation you need to use when what you have is you've summed the moments about a specific point, and that specific point is just somewhere. Got it backwards, didn't I? M, R, G with respect to O, crossed with A. Sorry. AO plus I about O times alpha. The first simplification that we can make is, let's say if the origin is fixed, you summed the moments about a point that is not moving. You know it. It's not accelerating. It's not moving. Nothing. Then if the origin is fixed, we have that the acceleration of the origin is 0. And so the sum of the moments about that point is just equal to the moment of inertia about that point times alpha. If the origin is the center of mass, also known as G, that means RG with respect to the origin. Let me fix this. This is going to bother me. That means RG with respect to the origin is the 0 vector. If that's the 0 vector, then we get almost the same result as before. We're summing the moments about, well, since the origin is point G, we're just going to say the sum of the moments about the center of mass is equal to the moment of inertia about the center of mass times alpha. For this one, that first term was 0, but for a slightly different reason. These are our 3 versions of the equation. There's this one, which you use in general when you're summing the moments about just some point. There's this one, when you are summing the moment about a fixed point. And this one, when you're summing the moment about the center of gravity. Summing, I'm going to write all these down. Summing moments about a fixed point. This is summing moments about any point. And this is summing moments about center of mass. The most common mistakes and general confusion on this topic in general is using these equations when they don't apply. Students want to use the bottom equation all the time, and they use it when they're summing the moments about just some point, and you can't. If you're summing the moments about a point that is not fixed or is not the center of mass, you must use the top equation. So the top equation is what naturally came out of the derivation for us, but for reasons that we'll see later, in terms of how we use these equations to solve problems, it is not in a particularly convenient form. The reason is what we're going to be doing in problems in general is we'll be summing the forces and summing the moments. And when we sum the forces, what that gives us is the acceleration of the center of gravity. If you know all the forces, then you use Newton's second law to find the acceleration of the center of gravity. And the top equation, this is the general moment equation, the one with the terrible asterisk on it. This equation here. The top equation. Hopefully you see it. The top equation is not in a convenient form because it's in terms of the acceleration of the origin. And if we use Newton's second law to find the acceleration of the center of mass, we don't know the acceleration of the origin, and then we have to put it in terms of the acceleration of the center of mass, and we've got to use kinematics, the chapter 16 stuff to figure that out. And it's just not great. It's not great. So what would be nice is if we could put this top equation in terms of the acceleration of the center of mass. This term is what we would like to fix. The derivation for the second version of the general equation is, it involves things to do with moments of inertia, and I'm not going to go through the derivation of moment of inertia on this video. So I'm going to write down the final result. This result, what you ought to know, is that it is mathematically the same as the equation on top. It is the same equation, and for that reason, you can sum the moments about any point you want to. It is going to look different. It is mr g with respect to O cross the acceleration of not point O, but point G. That's convenient, plus the moment of inertia about point G times alpha. Two things changed in this equation. Acceleration of g changed, rather, acceleration of O changed to the acceleration of g, and the moment of inertia about point O changed to the moment of inertia about point G. You can't just change those to whatever points you want. These two equations are only equal for the origin case and for the G case, which is convenient. I suppose what I just said is not true, considering the origin could be anywhere. Anyway, the important thing here is that this bottom equation is can be derived from the top equation, and it involves some somewhat tricky math. It involves the parallel axis theorem. It involves what it takes to move the moment of inertia from one place to another. It's rather involved, as I said. These two are therefore the general equations that we are going to be using the most. These are the useful equations. We will be replacing the second equation, the sum of the moments equation, with either this equation or this equation when convenient. When convenient. So, with that said, I'm going to conclude this video, and we can start talking about solving problems.